Happy Friday. We are diving into just a fascinating engineering story today. It really shows the gap between what tech can do and what it can, endure.
Right.
So get this. The headline is just stunning. Humanoid robots from Figure AI helped build over 30,000 BMWs.
30,000. It's a huge number.
A huge number at their Spartanburg plant. And then after just 11 months, they were retired. Pulled off the line.
Yeah, and it's so important to frame this correctly. This isn't really a story of failure. It's a story of learning.
Learning at industrial scale.
Exactly.
Yeah.
This is that moment where the cutting-edge tech meets the chaotic, dusty, just relentless reality of a factory floor.
So that's our deep dive today, the Figure AI pilot. We're going to look at what they achieved, but also the very specific technical lessons that led to that early retirement.
We want to synthesize what they learned from this deployment.
Because it's not just about the cool robots. It's about the brutal metrics of durability when a robot stops being a lab experiment and starts being a 10-hour-a-day employee.
Hey, if you like this kind of breakdown, please subscribe to the channel and definitely share this deep dive.
We should really frame this as a historic benchmark. I mean, this was the first time humanoids were doing real, continuous factory work.
Monday to Friday, 10-hour shifts.
Right. And that duration, that is what matters most here.
Okay, so as we unpack this, here's a question for you to keep in mind. What hidden costs do we underestimate when we take robotics from that perfect, clean lab and throw it onto a chaotic factory floor?
It's the big question.
So, okay, let's get into it. The company is Figure AI, based in California. They deployed their Figure O2 robot at the BMW plant in Spartanburg.
And like you said, it was a real commitment.
Right, this wasn't some 2-week demo they filmed for
a sizzle reel, yeah. This was 11 months of just relentless day in, day out assembly line work. And you said the duration is the key. Why is that so crucial here?
Because the pilot absolutely proved the robots can do the work. They can handle the processes, but the factory floor, I mean, with the dust, the constant vibration, the temperature swings, it is a profoundly tougher stress test than anything you could ever simulate in a lab.
Exactly. So let's look at the metrics first, because the output numbers, they look phenomenal.
Oh, they do.
They really suggest, immediate success. The scale is impressive. The Figure O2 units, they helped produce over 30,000 BMW X3s.
30,000 vehicles in 11 months. It's a huge number.
And to do that, they had to be precise.
Incredibly precise. The sources say they loaded more than 90,000 sheet metal parts with, real consistency. These are massive productivity numbers. They validate the robot's basic capability.
Yeah.
But then you have the other metrics, the longevity metrics. And that's where the full story is.
Right. So we know the service was 11 months. In that time, they logged over 1,250 runtime hours.
And think about the physical stress. They estimated the robots walked something like 200 miles inside that plant.
200 miles.
It's just a powerful contrast, isn't it?
Yeah.
We celebrate the 30,000 cars, which is great.
Yeah.
But it was done over a very specific, very finite lifespan.
So that 11-month limit becomes the key data point.
It becomes everything. It highlights this huge durability gap between where the tech is now and what you expect from a human worker who,
Who lasts a bit longer, as the source material put it.
Thankfully, yes. A bit longer.
Okay, this is where the story gets almost visceral for me. The CEO of Figure AI, Brett Adcock, he shared these photos of the robots after the deployment.
I saw those, yeah.
And they were just covered in scratches, scuffs, lubricant, grime. They looked like they had actually put in the work.
Absolutely. And that's what I call a definitive badge of honor.
Badge of honor. I like that.
It proves this was a real industrial deployment, not some staged photo shoot. It proves the robots endured demanding, physical, repetitive work. I mean, factory work means you're rubbing up against the environment. There's dust, lubricants, you're going to get bumped. It all looks deceptively easy in a clean lab video.
The environment fights back.
It does. And the robot wears the scars.
So despite looking so battle-worn, how did they actually perform, functionally in terms of pure precision while they were up and running?
That's the impressive part. They were remarkably good, over 99% placement accuracy.
99%.
And they were consistently hitting these tight 5mm tolerances you need for car assembly. That's machine-level consistency. That's the whole point.
And they kept up the pace. An 84-second cycle time, with about 37 seconds of that being the actual sheet metal loading. The operational goal was pretty ambitious, too. 0 human interventions per shift aimed.
And aimed is the key word there. You picked up on it. The sources are pretty clear that getting to that zero intervention goal took, and I'm quoting here, heavy lifting. So the precision was there, yes, but reliability was the real challenge.
So performance was great when everything was working.
Exactly. But the fact that they needed that heavy lifting, that human oversight, it points directly to things going wrong.
Yeah.
Glitches, failures, things that needed a reset.
Okay, so that's the big question. If the precision was 99%, why retire them early? What was the Achilles heel? What broke first?
The factory reality, it just ruthlessly exposed the weakness in the one area with the most demand.
Which was?
The forearm. It just emerged as the main source of failure, over and over.
The forearm. Why there specifically?
Well, it's where everything comes together. You have this complex combination of dexterity, strength, and just constant nonstop motion. It was a critical vulnerability.
What was it about the forearm that made it so fragile under that kind of stress?
So we've seen three key factors. First, you've got complex wiring that's running through a joint that is always flexing and moving.
Constant stress on the cables.
Constant. Second, the dexterity it needs puts a ton of stress on all those small internal components. And third, and this is maybe the most important one, thermal management issues.
Heat.
Heat. When you have that continuous motion, you build up heat internally. And in a tightly packed forearm, there's nowhere for that heat to go.
So it's not just the factory being hot. The robot is basically cooking itself from the inside.
Precisely. Your microcontrollers, your sensors, they start to fail when they overheat. These are all problems that just never, ever show up in short, cozy lab tests.
That is a fascinating insight.
It's the core difference, right? The lab test, if it can function. The factory test, if you can survive cumulative self-inflicted stress. The constant vibration, the dust, the repetition. Those are the real tech killers. And the forearm, being the primary point of all that stress, it always gave out first.
It makes you wonder, and here's another question for you listening. How can design teams even simulate that kind of cumulative stress without just doing this, without just running the hardware in a real factory?
And the answer seems to be, you can't. You have to deploy it and learn from the failure.
And that's the value of this pilot.
Absolutely. The early retirement sounds like a failure, but it was actually step 2 in a really important 4-step engineering cycle. It was the cost of getting data you could never get on a test bench.
Okay, let's walk through that process, because Figure AI clearly used these hard lessons to move right on to their next model, the Figure O3.
That's the engineering mindset right there. Step 1 was the Figure O2 deployment, which exposed all these weaknesses that were invisible in the lab.
Step 2 was the retirement and the exhaustive analysis,
which is where they identified the forearm as the main culprit. Then step 3 was the Figure O3 development, where they made critical hardware changes based on that data.
So what did they actually change in the new model?
They completely redesigned the wrist electronics. And crucially, they eliminated what's called dynamic cabling.
Okay, what is dynamic cabling?
So it refers to all the internal wires that have to constantly bend and flex as the robot moves its joints. Over thousands and thousands of cycles, that bending causes fatigue and eventually breakage.
Right.
By getting rid of that, or simplifying it in the Figure O3, they achieved a huge jump in reliability.
That is a major hardware change based purely on 11 months of real-world stress.
It is. And that leads to step 4, future deployment. Now you have robots that are built from hard-won, real-world experience. It's the cycle. Fail fast, analyze faster, build better.
And that pilot, even with its 11-month lifespan, it becomes foundational for the next generation.
Absolutely foundational.
So meanwhile, you have BMW. Despite this failure, they are still all in on this technology. What's their long-term strategy here with their iFactory vision? Why bother with robots that only last 11 months?
Because BMW knows this is a long game. Their commitment is really based on 3 strategic goals.
Okay.
First, and this is a big one, improving ergonomics. They want to automate the physically demanding, repetitive tasks to reduce strain on their human workers.
Which is huge for worker safety and retention, a massive cost center.
Exactly. Second is to gather insights. They need to learn how to integrate these flexible, multi-purpose robots into their already complex production lines. It's a systems problem, not just a hardware one.
And the third?
Refine communication. Improving how robots and humans coordinate, how they work together, and, importantly, how they troubleshoot when things inevitably go wrong.
So this brings us right to that core question for the human workforce. Is this collaboration or is this competition?
Well, for the foreseeable future, it absolutely reinforces the collaborative vision.
You think so?
I do. I mean, robots are great for repetitive tasks. We saw that. But this pilot proves that humans, we are still the undisputed gold standard for durability, adaptability, and longevity.
Based on these metrics, yeah, we are clearly still way ahead of the machines in terms of just endurance.
Vastly ahead. Humans work for decades, not 11 months, before needing a complete overhaul. And think about how a human adapts. You give a person a new task, they learn it from a sentence or two. The robot needs a complex firmware update,
A whole retraining.
a whole retraining. A human gets a minor strain, they take an aspirin, they keep working. The robot's equivalent was a thermal shutdown and a complete forearm redesign.
That flexibility, that ability to just troubleshoot on the fly without a reboot, that's the real difference maker.
It's the judgment, the flexibility, the longevity. Those are the assets robots are still chasing. The future, for now, is collaborative. The humanoids handle the physically taxing stuff, and humans handle the judgment and complex problem solving.
The tech just isn't durable enough to fly solo yet.
Not even close.
That really is a powerful summary of what this deep dive tells us. The Figure 02, it built over 30,000 cars, handled 90,000 parts, walked 200 miles. The scratches and scars, they prove it was a real working machine. But the reality of that factory floor is just demonstrably harsher than any lab.
I think Figure AI set the stage for the revolution by taking that first necessary step and, enduring that inevitable breakdown. But the takeaway is clear. This technology is improving like crazy, but humans are still undefeated.
At least when it comes to industrial durability.
Your job is safe, at least until, Figure 23 hits the assembly line.
Ah, that's the perfect benchmark. And you see the jump from F.02 to F.03, that's the real success story here.
It is.
So if durability is the main barrier, let's leave you with a final thought for the weekend. What single breakthrough is it in material science, maybe true self-repair, or just radical simplification, is most critical to getting a humanoid robot's lifespan from 11 months to 11 years?
A fascinating engineering puzzle to think about.
It is. If you want more deep dives just like this one, make sure you hit the like button and subscribe. We'll catch you next time.